Hi everyone, I'm Shuming Bai from Duke University. Today I will give a talk about our recent research on how to use molecular orbital overlap to describe the coupling of Dexter energy transfer and help the molecular design. A Dexter energy transfer is a type of a transfer reaction between the donor and acceptor where the globe spin of the whole system is not changed, but the spin of the donor and acceptor are both changed during the reaction. For example, in triplet energy transfer reaction, we need a Dexter mechanism, which means we need a spin exchange between the donor and acceptor to make it happen. And this reaction is important because the triplet T1 state usually has a relatively long lifetime so that it can provide enough time to make some excited state dynamics and reaction happen. Because of that, Dexter energy transfer have a lot of applications, especially in energy science. For example, we can use it to transfer the energy from photon harvesting position to the reaction center. People already studied the Dexter energy transfer between the nanoparticles and organic molecules, and this transfer reaction is also important to singlet fission problems because singlet fission will first generate the triplet pair, and then we need the Dexter transfer to separate them and generate the triplet excitons from the singlet fission. For Dexter energy transfer, the coupling is a key parameter because according to Fermi-Gordon rule, this diabatic electronic coupling will determine the reaction rate a lot. And this coupling is very sensitive, or it depends on the geometry a lot because it comes from a short-range interaction, and the orbital overlap between the donor and acceptor is required to generate effective coupling. So we want to have an easy way to predict the coupling change along the geometry, like the special factor of the coupling, so that we can provide the guidelines of molecular design to turn the coupling and the rate of this reaction. For the coupling of Dexter energy transfer, previous researchers have shown that the coupling can come from different pathways. Like in DA system, the coupling can come from a direct two-particle pathway, or it can go from a one-particle pathway through the mediated charge transfer states. So the whole coupling can be divided to two parts. For the DBA system with a bridge molecule, then there are much more pathways and the quantum interferences between them. So the question is, could we have an easy way to describe them without full quantum chemical calculations? In fact, people already use a molecular orbital overlap to describe the electronic couplings. Like in charge transfer problems, you already find that the electron transfer coupling can be described very well by the LOMO overlap with a constant factor, and the whole transfer can be described by a HOMO overlap. If we can extend this relationship to the Dexter energy transfer, we find that for the one particle component, the coupling is expressed by the charge transfer coupling and the charge transfer state energy. And then finally, it can connect to the product term of the two overlap terms, the homo-homo and the LUMO-LUMO overlap. And the two particle component can also connect to the same terms with the approximation of averaged separation distance. Then we can connect the co-coupling of Dexter energy transfer to a product term shown here, a product of two molecular orbital overlap terms, the homo-homo and LUMO-LUMO overlap with a factor kappa. And this kappa is a function of constant and charge transfer state energy and approximated distance term. So we can treat it as a constant if the donor-acceptor intermolecular distance is not changed much. And we have to mention here that the relationship shown here is valid only when the two front molecular orbitals are enough to describe the excitation of the donor and acceptor molecules. If there are more than one excitation configuration for the donor or acceptor, then there are some other molecular orbitals are not ignorable, then we have to consider more than just this term. There will have more overlap terms than just this one. We test this relationship with the real molecular systems. We start with a naphthalene dimer as shown here, and we take two frontier molecular orbitals as these two. They are from a simple DFT calculation of a single naphthalene molecule. And we calculate the coupling and the overlap term along the x direction. And as shown here, the coupling is reproduced very well by the overlap term. All the oscillation shapes are reproduced, and even the magnitudes are excellent if the distance is not too large. And this is because both the charge transfer coupling and the two-particle coupling can be reproduced very well by the corresponding overlap terms, so that each part of the Dexter energy transfer coupling can be described very well by the overlap. We also move the molecule along the XY dimension in 2D space and calculate the coupling and overlap term. As shown here, still the performance of the overlap is very good. All the peaks are reproduced, and the magnitude is excellent except for the long distance region. Then we test it with a covalent dimer. We take two fluorine units and connect them with a sigma bond in the middle. And we take two frontier molecular orbital from a single molecule, and we change the rotation angle in the middle and calculate the coupling and overlap term with a constant kappa. And as shown here, again the coupling is reproduced very well, nearly exactly by the overlap term along the change of the rotation angle. For the more complicated DBA system with a bridge molecule in the middle of donor and acceptor, we know there's much more pathways. But for the dominant bridge-mediated pathways, then the the bridge molecule are involved in the pathways, we use the same strategy, and finally we found that the coupling of these pathways are connected to the same overlap term, a product term of 4 overlap terms with kappa as a factor. We also tested it with a real molecular system by taking ethylene molecule as a bridge in the middle of naphthalene dimer and take its frontal molecular orbitals to calculate the overlap term. And we calculate the coupling and overlap along the x and y direction. And as shown here, the overlap can tell the right main peak of the coupling with the right position. Although there's some peaks in the coupling are missed in the overlap term, and the magnitude is not as good as in DS system. This is because we only consider the bridge-mediated pathways and ignore the other pathways like through-space pathways. So there are some details not reproduced by the overlap, but still this overlap tells the main peaks, which is the most important for us. As a conclusion, we find that the coupling of Dexter energy transfer usually can be described quite well by the corresponding molecular orbital overlaps between the donor and acceptor. Like for DA transfer, we only need 2 orbital overlap terms, the HOMO-HOMO and the LOMO-LOMO overlap, to describe or reproduce the coupling of Dexter energy transfer with a constant factor. And more important, we only take the molecular orbitals of single molecules. So we can get them from simple quantum chemical calculations, which is easy even for a lot of experimental groups. And we can use it for complex systems like large molecules and nanoparticles. And with our approach, we can predict or screen the coupling along the geometry change of the system and provide the guideline of molecular design to turn the coupling strength. Finally, I want to thank the support from Bratton Group in Duke. I want to thank Professor Bratton and Professor Zhang, and our collaborator from Cyprus, Professor Skouroutis. And I want to thank the grant from U.S. Department of Energy for the support. Thanks you for your attention, and I look forward to your questions and comments. Thanks.